So, um, so uh, So the context research is a tool, the conception of tool and method for interpretation and musical performance. Actually, the same research field as talked with just before. So because we don't trust to people that are computer scientists, we want those tools and methods to be simple. And because we are computer scientists, we want them to be reliable. So we need some to formalize properly the things that we manipulate. In this field, we have already some models such as Polydax polymorphic temporal media that are implemented in TRP. So in polymorphic temporal media, we have simple media that can be anything such as audios, videos, MIDI audio. Well, I don't know what. And we can compose it either by sequential or in a parallel way. So, but the problem is if we want to describe phenomena that have several structures involved, such as in Bob Dylan's song "Blowing in the Wind," then the music and the lyrics have difficult structure, and we would like to be able to express how those structure interleaves. For instance, here you can see the lyrics of the song, where the red bars correspond to the musical bars, and the curly things below just look like express the grammatical structure of the lyrics. And we would like to be able to represent both structure in a single model. So if we group the lyrics by grammatical structure and synchronize them according to the bars, then we have such a structure. We can do it either by bars or by 4 bars, and then we have we respect the verses decomposition of the song. So this suggests that we could simply enrich the polymorphic temporal media with 2 markers that will express where the things that come before will be synchronized and where the things that come after will be synchronized. And then we can define a product on this model. So first we align the pre-marker of the first, of the last element of the composition with the post-marker with the pre-marker. Well, you just... So our goal is to write a player for for those tiles. So we want it to be real time, and we want it to be polymorphic, such as it handle various media types. So we first need to start from an implementation of those tile polymorphic temporal media. So thank you. Here's the syntax for constructing such those tiles. So we can define it in terms of delays that can be either positive or negative, and events that can be a media event, for instance. So with this syntax, we can describe a zigzag tile. It means that in the syntax, we don't have to reflect the temporality of the event, meaning that we can say, I start here, in 1 second I will have an event A, but 2 seconds before an event B, then 2 seconds after an event C that will be at the same time as the event A, and so on. And the time goes from left to right. But if we want to compute a rendering of such a tile, the first event to occur can be deep in the structure, so we have to normalize it. And in order to do it, we have an algorithm. Well, those 2 tiles are equivalent because they render exactly the same way. So we have an algorithm defined in terms of AT and TLT that are named after the the function on the list, because the head T will extract the first event and the first delay, and tail T will return the remainder of the tile. And so a normal form will be defined as the head of the tile and composed with the head of the tail of the tile and composed with the head of the tail of the tail of the tile, and so on. So we see that in order to be able to compute on-the-fly real-time rendering of the tile, we need to have an efficient implementation of head and tail. But with the syntactic representation, we have two problems that comes to us. The first one is that for a given tile, we can have an arbitrary number of delay, because this relation holds all the time. And so, for instance, with the code that I start with, the implementation of tail T actually increased the number of delay in the tile. So when we started to compute the rendering of the tile, it's just worked, but when we took the tail of the tails and the tail of the tail of the tail, etc. of the tile, the size of the tile increased, and then we have such a degenerate performance. The second problem is that the expression of the tile matter. When if the users, for instance, define a tile with only positive delay and which is right parenthesed, then the first event to occur will be deep in the bottom of the syntactic structure. So we have such a curve because the first each time we the time of sorry. A friend of mine told me to imagine that you are cabbages. That's actually seeing a bunch of cabbages sitting in chairs and staring at you isn't that comfortable. So with our proposed implementation, we guarantee that the number of delay is linear in the number of events. Actually, the number of events is the upper bound for the number of delay, and the structure is balanced. So when for this graph, with the same type of this graph, with this implementation, we have this one, so it's pretty much better. The principle of this implementation is to forget the syntactic representation of the syntax that defined the tree, the tile, and well, for the tile we need the markers that say how it's synchronized in its context, and the set of events, of timed events that compose it. So we just represent it like that. For the code, which is just a pretty straightforward implementation, and the duration is a type synonym for rational, actually, and SHEAP is Slater and Sargent's QWIP. It's so it's a binary tree where the nodes are indexed by the duration, and they embed a multi-set of events. We can see here the correspondence between the syntactic representation as shown before and this implementation. So here you can see that all the events are placed relatively to the premarker of the tile, and the only negative delay that is allowed in the tree is the first one. Usually in QWIPs we we use absolute time for expressing the things, but here with relative time we have a good property that will matter later. So for the product, we just take two tiles. So here we have a first one, and we have a second one that is aligned with the post marker of the first one. It's the meaning of the shift skew heap call, and then we simply merge the heaps and the duration. So the main reason, the good algorithmic property of the skew heap is made by the implementation of this merge, because a skew heap verifies the property that all rightmost paths are short, and if we want to insert something, if we want to merge to tree, then we do it following the rightmost path, but when we swap the child, we actually merge the heaps in the inside of the tree rather in the rightmost path. So with this, it's amortized complexity, so technically it's possible to have a linear operation, but if we have, so it means that we had just before a lot of constant time ones or short one. So we have a logarithmic complexity for the composition and the tail call, and the head call is in constant time. And for the space complexity, it's the number of events. A world of on infinite tiles. With the syntactic representation, the duration of the tile is exactly the sum of all the delays that compose it. So if we have an infinite tile, then in order to have a finite time, we must have another infinite delay, but in the other way. So such a sum will diverge. And we will have some memory leaks if we try to render such a tile. But with this implementation, as we have not correlated the duration of the tile and the delays that compose it, then we can simply have an infinite tile. And that's all. Thank you.
Questions?
On the graph you showed, the last one with the performances of the fast algorithm, there are a few outliers, some points that are well above the other. And at this point I asked why, and then later you said that your algorithm is amortized. So there are some.
Yeah.
Do you know whether the point that we see here?
Those ones are just garbage collectors.
Can you repeat the question, please?
Yes. The question is what are those points that is above the bottom ones? And the answer that is it's a garbage collectors. Sometimes it triggers and it's done some style, and actually some few are above the.
So this is not related to the amortization part?
No. Well, the case where we have the degenerate case of skew heaps are very tricky to get. So basically, if you want to build a degenerate case for the skew heap, you have to do it on purpose.
More questions?
So, how did you settle on using skew heaps as your abstraction practices?
Well, I just figured out that it looked like a heap, and that I needed a heap, and skew heap an implementation of skew heap can be done in about 10 line of Haskell. So, and it's a very nice data structure.
Are there cases where you know the music statically, so you can solve the problem at compile time instead, maybe with template Haskell, or
I don't understand.
as it, you're doing this at runtime?
Mhm.
Are there instances where you might, like, did you consider template Haskell in some cases to statically do that at compile time?
Well, in further research, we would have to be able to make the sync interactives. So we try not to we try to do the computation of the tile the later possible. In order, because we may don't know when we will know when we have to do it.
Okay, one more question over there.
Last year, when recursion was a problem.
I think you need to speak up a bit.
Is recursion still a problem if you're trying to represent something that is recursive?
If the question is, how do we represent recursive tiles?
No.
Is it a problem or not to do infinite tiles and recursive tile? That was a question that was addressed like last year in multi-type papers.
Well, the problem is still the same.
Okay.
It doesn't make any progress in this direction.
So then let's thank Simon again. Thank you very much.